For today's video, I am starting a new series where I go through detailed solutions for past STEP papers. If you do not know already, STEP stands for 6-term examination papers and has been a required admission test for entry to undergraduate degrees in top universities such as Cambridge. Without further ado, let's present the question. In part 1 of the question, we have to find all positive integer pairs, NP, which satisfy the equation n factorial plus 5 equals p, where p is a prime number. Now, looking at this, the usual method of solving equations wouldn't work. This is not a quadratic or cubic equation, which we have been used to in schools and exams, so a new approach is needed. The fact that p is a prime number is important. A prime number can only be divided by 1 and itself. Let's see ourselves what values n can take, given that p is a prime number. If our n is an integer equal or bigger than 5, then n factorial would definitely be divisible by 5, and we could then factor the left hand side into two non-trivial factors, one of which is 5 and another of which is bigger than 1. This violates our assumption that p is prime, creating a contradiction. Therefore, we must have n less than 5, and by checking cases for n equals 1, 2, 3 and 4, we see that 3 of these cases actually work. We obtain the pairs of solutions 2, 7, 3, 11, and 4, 29. One thing you will notice about step questions is that the first part of the questions are usually somehow related to further parts of the question itself. The examiners usually provide an easier example or special case to the candidates, so they will be able to ruminate and reflect on the new techniques introduced before pushing for more creative use and applications of the initial idea introduced. You will see what I mean later when we move on to the second part of the question. So in the second part, we need to find positive integers m and n, which satisfy the equation 1 factorial multiplied by 3 factorial and so on until 2n minus 1 factorial equals m factorial. We are given two results we can use. The first one gives us a lower bound straight away for us to work with, the left hand side of the equation. While the second result, which says that there's a prime number between 2n and 4n, is rather famous and is better known as Bertrand's postulate. Using these two results only, let's try and solve the equation above. I guess the first obvious thing to do is to say that m must be greater than 4n, using the first inequality. Okay, all is well, but what do we make of this and what do we do next? This is when the second result is useful. If there's a prime number, let's call it p, between 2n and 4n, then since m is greater than 4n, m factorial, which is a product of the first m consecutive integers, must be divisible by that prime number which is between 2n and 4n. If the right hand side is divisible by p, then the left hand side must be divisible by p as well. However, the left hand side is made up of products of numbers which are all less than p. Since p is a prime number, we cannot simply create it using a bunch of factors which are less than p. We therefore draw the conclusion that there is no positive integer solutions to the question. However, before we can celebrate, we should hold our horses. If we check more closely, the first inequality only holds for number n equal and above 7 only. This is when the situational awareness comes into play. If we have not been careful and straight away declare that there's no solution for all n, then we would have certainly lost a lot of marks there. This is another reason why we should always keep in mind that the work we have done earlier in previous parts of the question will always give us a hint how to proceed. Remember that in the first part of the question, once we concluded that no solutions exist for n greater or equal to 5, we do check in manually the cases n equals 1, 2, 3 and 4. The same logic comes into play here, so we have to check a few cases. The case for n equals 1, 2, 3 are trivial, and we can find the required answers straight away. To see that n equals 4 works take a bit more work and calculations, but we eventually see that it equals 10 factorial by grouping factors. Now, we have these two which remains to be checked. We know that 1 factorial times 3 factorial times 5 factorial times 7 factorial times 9 factorial must be greater than 10 factorial, the previous product. But going beyond 10 require a factor of 11 on the right hand side, which the left hand side of an equation cannot provide. So we can conclude that n equals 5 does not work. Finally, we can check n equals 6. The left hand side is divisible by 11 factorial, so on the right hand side, m must be greater than 11. However, m cannot be greater or equal to 13, since 13 as a prime factor does not show up on the left hand side. This leaves only one choice for m, which is 12. But clearly, the equation does not tally when m equals 12. So, n equals 6 does not work as well, and we are left with only these 4 as our final solutions. I guess when solving step questions, the tricky part is always to figure out the message the problem setter is trying to send you. Always ask yourself why they ask you to prove a seemingly easier question or result, and try to expand the idea or generalize the result given in a clever way. The question above is a classic example of the central ideas, which is essential for success in STEP exams. Okay, we have come to the end of the video. I will continue with this series, and I will see you in the next one. Until then.